giant, and why this is interesting for the angle of the models, right? Most of the people in this conference I know is expert in models of galaxy formation and evolution, and it's time at last to talk about these lows of the brightness galaxies in the perspective of models. Perhaps 20 years ago, even less, I mean, 8, 10 years ago, it was very difficult to model this kind of galaxies in the context of galaxy evolution. But in the recent years, there has been a lot of inputs from the observation side, these ultra diffuse galaxies, and also from the side of models, as I will show you. So let's start. This is the outline. I will try to stick to the half-an-hour presentation. You are going to tell me if I can keep to that. So first, we are going to start with definitions and properties. Not everyone knows what these galaxies are. The relevance of these galaxies in the context of galaxy formation evolution. We will talk about the path from the general laws of the brightness galaxies to the giant ones. Then I'm going to talk about some observables that should be constrained by models in principle. Some clues with the models we have nowadays about the formation of these giant LSBs, and then conclusions. And of course, open questions are very welcome at the end. So some definitions very quickly and some properties. What is a low surface brightness galaxy? In simple, it's just a galaxy with a surface brightness which is fainter than the night sky brightness, right? This is about 22.5 magnitude per square second in the B band. Of course, if you go to a very dark site, you can obtain even a little bit less brightness. Well, the simple definition that you see above, in fact, carry also other consequences, which is studied in this field in the last 20 years. And some of them are especially interesting because they, in principle, can hidden doubts and open questions in the context of galaxy formation and evolution. Some of them are the following. First, you will find low stellar formation rates in most of these galaxies, which in fact means in the general side that you lack or you have a low molecular gas density in general, okay? Also, you can expect, and you observe usually large H1 fractions, little bit 30–20% more than you observe in high surface brightness galaxies, spiral ones in general. Also, you observe in most of them very flat and very extended rotation curves. The work of Stacy McGough, in principle, and the blog in the 90s show very much this behavior. So you expect large fractions of dark matter in these galaxies. And usually this is accompanied by a high specific angular momentum. I will talk about this especially in a few minutes. Another interesting property that is very interesting to be studied with the models of galaxy formation and in the cosmic web is that most of these galaxies are relatively isolated. Generally, they are not part of rich or dense groups. However, it's interesting to point out that these ultra-diffuse galaxies rediscovered by Van Dokkum in 2015 lies in clusters, right? So, but these galaxies in general are not giant, are not large LSBs, regardless that Van Dokkum even entitled the paper in 2015 like something like ultra-diffuse galaxies of the size of the Milky Way. But in fact, less than 10% of these galaxies are of the size of the Milky Way. Most of them are dwarfs. Okay, so why these galaxies are relevant? First of all, they dominate the volume density of galaxies and the universe. That means if you take a volume, whatever the size, and you count the galaxies in that volume, most of them are galaxies of faint surface brightness, right? Here you can see the plot. This is a compilation made, in fact, made by O'Neill in 2000. Up to date, many people is putting points in this graph, but roughly speaking, is still very, very current. Okay, so you see in this plot most of the galaxies are in fact LSBs. That means galaxies fainter than 22, roughly speaking. So if you take a galaxy in the volume, the probability that is an LSB is very high. Okay. Also, they dominate the stellar mass. Okay, of course. Here you see, well, this is the typical luminosity function. I have cut this plot. Okay, that you observe typically at high surface brightness magnitudes. Okay, brightness, and this is about 10 to the 10, 10 to the 9.5 solar masses. But when you go to very faint, to very low masses, you observe these kind of things. The luminosity function or the mass function is still increasing up to very, very faint magnitudes, and also lower masses. This is all the compilation of the many things. This is a plot from the Wide Area Vista Extragalactic Survey. I failed to put the reference, sorry for that, but it's taken from a publication. Then another interesting thing is always talking about this mass end. Here you see a very interesting plot by Muñoz, 2015, from the Next Generation Fornax Survey, led by Thomas Pusia here at Católica. Here you observe clearly that when you go to the low surface brightness side, that means these straight lines here, say 24, 26, 28, you really observe a completely different realm in the universe, in the extragalactic domain. So most of the galaxies that dominate this faint end in the surface brightness domain are dwarfs, are galaxies very diffuse, ultra diffuse, and also some galaxies that are very large. Yeah, these very large galaxies, in fact, are there here in the upper right side. Right, as you can see, there are few of them. These galaxies are not very observed in this, of course, in this survey in Fornax are not there. But when you go to the field, you can start to put some galaxies here. I will show you that Malin 1 is one of these galaxies that lie at the very end, very bright, absolute magnitude because it's very large, but very low surface brightness in this galaxy. This galaxy should be normally here, right, at the far upper and right end. You can, of course, disentangle more things here. You can see here the globular clusters. You see ultra diffuse galaxies generally here, and normal spirals are there, right? So again, these giant low surface brightness galaxies lie at the upper right end here, few of them, okay? So the path to giant LSBs is something that should explain how you form galaxies like ultra diffuse galaxies, dwarf galaxies of very low surface brightness and small size, to giant things. It's completely unclear how these things can form, but of course I will show you some insights from models recently obtained. Okay, so here you can see different dwarfs from the Next Generation Fornax Survey from Thomas Pusian. This is a publication by Paul Egenthaler, one of the collaborators. It's an excellent paper. I really recommend you to read this. And there they show many small LSBs in Fornax. Some of them are ultra diffuse, some of them not, because they are clearly normal dwarfs, but diffuse. And so it remains a very interesting study of these galaxies in the field. Most of the studies by Thomas and Paul and also by Van Dokkum show these galaxies in clusters. It remains an open question to study these ultra diffuse galaxies in the field, which is completely open. Okay. Well, talking about giant ones, this is the iconic giant LSB, which is Malin 1, was observed in the 80s, discovered by Botun and Dave Malin. They call them Malin 1. Then they appear Malin 2 and Malin 3 that are similar, a smaller one. They are giant, but not as large as this galaxy. It's a very special case. We are not completely sure. I will show that with models you can in fact, obtain similar galaxies like this. By the way, also it's also the largest spiral observed so far. So if you choose the largest spiral in the universe, you fall with this galaxy, and it's almost 200 kiloparsec diameter. So that means it's about 7 times larger than the Milky Way. There is no molecular gas detected so far. So one of the reasons why I'm here is that because I'm writing a proposal for ALMA for detecting gas in this galaxy. Many attempts fail, but we are hopefully we'll take this at last. Where's the gas is not clear, but it should be somewhere, because this galaxy has H1 in enormous amounts, and also many stellar populations in the whole Heston-Russell diagram. And also, we observed recently by MUSE, I will not show this now, but we observed H alpha in many spots. So the gas should be there. Many questions, you can ask many questions about this galaxy. Where is the gas? How is the gas? Which is the temperature, the density is completely unclear. Where is this galaxy located in the Krumm-Holz diagram that shows the gas density as a function of the stellar formation efficiency? It's in the very low end. And here you can see how this galaxy is. In fact, this image I showed before is an image from the Digital Sky Survey. This is the real, this is the galaxy, in fact, with all the spiral arms. We discovered that in 2015, and then Boissier also have another study with the same 1 year later with the spiral arms and the disk. It's really a very special galaxy, very interesting one, and many people are studying that now. So Boissier in 2016, studying this galaxy, suggests that there is a low evolution. I mean, this galaxy is evolving very slowly compared to normal spirals. And also, he showed that the angular momentum should be at least, roughly speaking, about 20 times larger than the momentum you observe in normal spirals. Well, let's talk very quickly about the observables that should constrain these models. What should be, how the model should be used to constrain quantities in this galaxy to be matched with observations. I will talk about that now. So the first thing is that the Krumm-Holz diagram is something that should be built by these giant galaxies. And some people has worked on this. Daddy in 2010 located some of these galaxies here in the lower left end, of course, in this Kennigat-Schmidt diagram, which is now it's called the Krumm-Holz diagram, but it's in fact the same as the Kennigat-Schmidt law. Here you see, and then the surface density of the gas, and when you talk about gas, it's a little bit tricky because you can include H1 and also molecular gas. For many galaxies, we have the H1 from for example, studies that measure H1 in galaxies. Okay, I forgot now the name of the typical survey, but high pass and others. Okay, this is easy. It's relatively easy, but to have the molecular gas for all the galaxies is very complicated, especially when you go to the low density side, of course. So here, Malin 1 is about, should be, nobody has measured the gas, I mean the molecular gas, but should be very in the low left end, okay? This is important, so that could be studied with models. It's not well determined, this distribution. Also is, well, I already talked about the molecular gas. Another thing that the models can constrain, because in the models you can see all the things turning around, is the dynamical time as a function of the stellar formation rate. Silk in 1997 showed that it's very important to constrain this to determine, for example, if the galaxy has time to evolve dynamically larger than, for example, the stellar formation rate. These two things should be related, as this plot of Daddy shows. This is important. Also, you can show that LSBs have probably, using the models, you can show that have probably the largest dynamical time and are very well separated from other populations. So that could be interesting to show, to be shown or to be verified with the models. Another thing that is important is the gas. Okay, so if models can really constrain the action that is suffering the interstellar medium in terms of the CO, that is interesting. And so from the observational side, we have detections of gas in some giants, but not of all of them. In fact, the first detection of CO in an LSB galaxy was made in 2000 by O'Neill, and then Matthew in 2001. And Malin 1, as I commented before, remain without detection nowadays. I will show some of the efforts made for this. For example, Brain in 2000 obtained this after about 30 hours using the IRAM 30-meter telescope in Pico in Spain. This is the result. So he reached, roughly speaking, between 3 and 5 millikelvin and no line. I mean, at this very low end of sensitivity, you really don't detect gas in this galaxy. There were other attempts I will not describe, but for example, there were many accidents, people that forgot or miscalibrate the radio telescope using another velocity. I mean, many things like that happen to some people. I will not enter into details, but the Brain, even if you don't detect CO in this galaxy, you can have a constraint for the upper threshold of the molecular gas mass. And if you take that into account, you arrive to the conclusion that the gas should be at very low densities and the mass gas should be lower than 10 to the 8.5, roughly speaking. So compared to other galaxies and taking into account the size of this galaxy, this is very few molecular gas. If you use, of course, the conversion factor that we observe in the galaxy and all the things, this is very tricky, by the way. So we observe to this galaxy using the GBT, the Green Band Telescope 100 meter with Argus, which is a very interesting detector with many horns. It's like a Pullman interferometer, right? And we reach 0.3 millikelvin and no gas. These are observations obtained perhaps 8 months ago or something, and we don't detect gas after almost 20 hours observing time with this very large telescope. So again, the mass should be even less than 10 to the 8 in the mass of CO. So no detection to 3 sigma. We changed the observing technique. Doesn't work anyway. So what is happening here? Nobody knows. Some people, I support this idea, think that given that this galaxy is very diffuse and there is no almost dust in this galaxy, perhaps the ISM is quite transparent, and then the ultraviolet radiation can really reach very far distances. And in general, because of that, the ISM is a little bit warmer than you obtain in typical galaxies. So we lack perhaps the shielding of dust from the UV radiation, and then the ISM is 10 to 15, even 20 degrees Kelvin warmer than you can observe in normal spirals. It's not sure what is happening here. In 2008, we support this idea, and up to now is perhaps what is happening. But there are some different opinions. Brain, between others, think that the ISM is in fact colder than in other galaxies. It's not, and then the models can, of course, help. The other important thing to be constrained by models in this galaxy should be the angular momentum. The angular momentum, all the evidence, observational evidence, show that the angular momentum in these galaxies is larger than observed in normal spirals. Why? It's not completely clear. Dark matter perhaps have a role here, of course, given that these galaxies have, in general, large fraction of dark matter because the rotation curves are very flat and are very extended. So fall in 2018 showed that using some data and some models, make a distinction between the pseudo bulge and classical bulge to explain, or hopefully to explain, why the angular momentum in these galaxies is large. Okay, so this is technical things. I will not enter too much into this, but FoF show that most of the galaxies have this alpha 2/3 to explain the specific angular momentum that is defined with this formula. Okay, the problem is that when you compute the angular momentum from general principles, you have to normalize. Okay, you have to normalize the angular momentum, and that depends in general when you pass to observations into the morphology, and there is a problem. So you can obtain some scaling relations. For example, Rancine in 2010 obtained this scale high that is show that is function of redshift. So you can even complicate or simplify the things, but it's not a simple thing. There are many different opinions about this, the angular momentum in LSBs. So another very interesting study that perhaps Pérez Montañó will show about this, talk about this, using Sloan. They show in a very nice publication in 2019 that, in fact, LSBs have larger angular momentum than normal spirals. Here you see different proxies for the angular momentum. They use 6 proxies using models and using data from Sloan. They show, statistically speaking, that in fact the angular momentum in LSBs is larger than normal spirals. Then we published with a student in 2021 some very a little bit odd publication. We take many galaxies, normal and LSBs, from the literature. We compute the mass. So we made a compilation of all we have, and we publish in one single publication the angular momentum compute from first principles and observational data for all the galaxies and compare. So again, we obtain the same. In fact, when you really uniform the things, you obtain also that the angular momentum of LSBs is larger than in normal galaxies. And this is reaffirmation of all the other publication that they are right. But no one has done this before. I mean, in each publication you obtain that, but using different things, these different surveys, different computations, and so it was not easy to uniform the things. But when you do that, you obtain, in fact, by that the LSBs are the angular momentum of LSBs is higher by about 0.17 dex compared to the angular momentum in normal spirals. Okay, so what next? Some question that you can or you expect to reach using models is how these galaxies form. Okay, how they evolve. The evolution is an isolation or not? Are these galaxies obtained by models are formed in isolation or not? It's not clear. So this is very important to be compared with models. Now we have Illustris, Eagle, and other things. I will show you some models, some results from Eagle that we did with Nelson Padilla and Andrea Culia, postdoc. We had some recent years. Now she's in Leiden, but still working on this. Also, you can see Sue in 2018 did a very nice job showing that you can form, in fact, a giant LSB from the collision of 3 galaxies, a normal elliptical, and then collided by 2 spirals. And you obtain a very large galaxy, a very large loss of a branch galaxy. In fact, very similar to Malin 1, for example. I will accelerate a little bit this presentation, but you can reproduce many of the things that you observe. The gas and the stars. Of course, the molecular gas is not derived in this simulation, but you can obtain the atomic gas, and it's roughly speaking is okay. Okay, they can reproduce most of the things that we observe in Malin 1. Also, an interesting thing is they have the cold gas, okay, within the simulation, and what they show is that the gas remains quite hot for many time, and then when you are near redshift 0, the temperature gas drops violently, very, very violently. So this is something that remains to be compared with other models, of course. With Andrea Coulier, we reproduce galaxies that are similar to Malin 1 using Eagle, which is an hydrodynamical model. And these are some results. These are images, I mean, synthetic images from the simulation. And in fact, we reproduce more than one. Okay, here you can see 4 galaxies that are quite similar to Malin 1. There's one galaxy that, in fact, is, roughly speaking, of the same size. The rest are, in general, smaller. Okay, I can show you some of the results. We can have the main result, the main value of various dark matter halo properties as a function, for example, of the central galaxy stellar mass. With the models, you can obtain many, many, many things. Andrea made an excellent job comparing, for example, the kinematical properties of these galaxies, the circular motion properties. There are some intricate graphics that I will show you. I will not enter into very details now, but you can go to the publication, Coulier et al. 2020. But in general, you observe the same observational things that you observe in giant LSBs. For example, the angular momentum tend to be higher in LSBs than in normal spirals. Okay, these are high surface brightness. When I say normal spirals, I mean high surface brightness spirals. Also, the rotational velocity tend to be high in LSBs. The baryonic mass tend to be a little bit higher in the central stellar mass, in the central mass, not in the periphery. Okay, there are other things here. I give you this for reading directly in the slide. Okay, you can compute the mean star particle distribution in projected radius, and also have this circularity parameter for galaxy that is defined like this. And Andrea defined a very interesting idea, which is the formation ex situ. That means when you have a galaxy that has been accreted most of the material, not in the site where the galaxy born, but as a consequence of many merging episodes. So what Andrea showed is that many LSBs, in particular giant LSBs, are formed after many more than the normal galaxies by many merging episodes. And this is very interesting from this model. I don't know what happened with Illustris, but perhaps it's not very different from that. Okay, there are other relations. Here is a very interesting plot to show, in fact, that LSBs, which are, when you plot the mass of the galaxy as a function of the surface brightness, you see that most of the galaxies are very, very low surface brightness in these plots are, in fact, formed ex situ. It's the same. It's pretty much the same as before, but in another representation. So in conclusion, this galaxy seems to be formed by a lot of merging episodes, and also they, in general, the models show that these galaxies are in the periphery of the filaments, are not in the center of the filaments in the structure. With Nelson Padilla and Ceccarelli, we showed that some years ago using models that, in fact, these galaxies are not.
Sorry, Galaz. I don't know what happened, but I think that the light is off here in the auditorium.
Yeah.
So give me a minute to solve the problem.
Okay. Sure.
Yes. In the virtual meeting, everything goes well.
Right.
Okay. So I can continue?
Just wait for 1 second because there is something in the auditorium.
Okay.
That is wrong.
Something you need, you mean a bird or something like that, or?
I don't know.
It seems there is a power cut, so they cannot see the slides, I guess.
Yeah, sorry, Galaz, but it's an electric problem here in the auditorium.
Okay, no worries.
I'm gonna update you about this problem.
Okay, you tell me.
Hi, Galas. We have a light again, but
Okay.
we are resetting all the audio on the presentation. So
Okay.
I am going to tell you when you can restart or
Okay. Thank
continue.
you.
Sorry.
Okay. Thank you.
It is funny because all the problems we normally have is that we have bad internet connection or something like that, but now are the in-person attendees that are not.
Yeah. No. Not worry.
Yeah.
Murphy's law are always turning around, so
Uh-huh.
no worries.
Oh, there is light in the camera.
We had some power cuts here in Santiago yesterday by night, so nobody knows what happened, but
Mhm.
they say that is because of the energy that we have no water and no
There's no rain.
hydroelectricity, not too much. So some people says this that but nobody knows for sure.
Now, is it done? Okay. So, Gaspar, can you hear me?
Yes.
Okay. So, please go ahead. You have 4 minutes.
Yeah. Yes, I am almost finishing. Okay, guys. Thank you, and well, no worries. So another clue that is important to solve with the models is that we have new observation from dark energy survey. This is important. There were a publication recently by Tanoglidis in 2020 about the LSBs from DES, from dark energy survey, and they have very nice results. One of them, for example, that should be perhaps explained by models is the two population of LSBs that are observed, red and blue. This was reported by O'Neill in 1996, and by a group we had at that time in 2002 using Sloan, in fact. We reported that. So the large-scale distribution of these galaxies is still remain something to study. Here we can see the red and blue population from this is quite notorious. Even in the image, you can see that they are red and blue. Okay, and they have very interesting things in the footprint, for example, of the distribution of these galaxies. These are the blue and the red, and you can see that the red galaxies, red LSBs, are quite concentrated in clumps. This is interesting. Okay. Well, you can, of course, study the correlation function, and this correlates the same. I mean, verify the same, that red LSBs tend to be more concentrated than or clustered than blue ones. Okay, so conclusions, I will finish here. I will put the conclusions right here to read, and this is all. Thank you very much.
Thank you. Questions?
Hi. If I didn't miss something, you showed two trajectories of in this simulation in TNG or Eagle. I don't know. I wonder how long you back in the redshift in time. I mean, it's the environment important in these situations for the final result?
Yeah, hi. I don't know who asked, but I didn't understand everything because the communication was a little bit split in parts. So can you repeat me the question again, please?
Well, see, don't worry. The I if is the environment in in the merge, if it's a merge, in the trajectories you showed before, and how much time do you see your interest in follow these members?
Okay, thank you. Yeah, I think I now understand. You mean by the trajectory, you mean this plot, no? Perhaps?
Yes, yes.
Okay. Yeah, this is from Sue. As far as I can remember, these are the redshifts, right? So you can see the trajectories here. These are the two intruders that are going to collide with the central galaxy. This is redshift 2. This is redshift 1.5, 1, etc. So you can see that the collision itself occurred just in the last minute. Okay, so if I can ask, I mean, I can answer your question. The ideal situation could be to trace, and you can do with the models, to trace the halos from the first moment when they start to fall and to collide and to merge into this kind of LSB galaxy. So you can do that with the models anytime. I mean, you can really, I mean, follow the whole trajectory of these things. I don't know what is the redshift resolution that you can have in these models. But one thing is true, that the collision itself is very rapidly compared to all the falling time of this galaxy into the central galaxy. So I guess that we want a very high resolution in redshift in time in this, because the collision time is quite rapid. If I understood correctly your question.
Yes. Thanks.
Yeah.
David?
I will go again to the camera to see the people there.
Hi, Gaspar.
Hi.
Avilaris. I would like to know your opinion if there is a controversy or not with simulations or semi-analytical models in what respects the abundance of LSB galaxies compared with observations. Is there a problem really or not? What's your opinion about that?
Yeah. Okay. Well, there are twofold answers I can give you. The first one is what the evidence show up to now from the observational side. Giant LSBs up to now are some rare things. They do not seem to be something that are over there in excess. I mean, many people is discarding this. I mean, are not supporting the idea that there are many giant LSBs and we are not just pure and simple don't seeing them. There seems to be not there. But another interesting thing is, and it's almost, and there is my opinion. It's my opinion. I think that we are missing some of them. I don't know why. Because perhaps with this, by the same reason that we lost Malin 1 for many years, up to the 80s. This galaxy was discovered because it was observed in the H1 data that there was a big spot of H1. And when they compared the spot in H1 of these galaxies, they discovered a teeny galaxy there, an optical one. And then they obtained deeper images and they discovered that it's a huge thing. They first discovered the gas of the galaxy, the H1 gas, which is enormous. And then they discovered that at the center of this big spot of gas, there was an optical galaxy, right? And then along the years, we showed that the galaxy, in fact, has an enormous amount of stars, a few amount of stars, but spread in a large size. How many of these galaxies could be there? I don't know. Personally, I think that one very nice way to discover these galaxies is to reach fainter and fainter limits in H1 in blind surveys, like High Pass or others like that. But up to now, the limiting magnitudes or limiting the limiting surface brightness in H1, the column density in H1 is still very bright. It's very high. So that means that we are not really discovering these galaxies in general in the surveys, in H1 surveys. So this is my opinion. So to discover more of these galaxies, perhaps it's better to have more sensitive H1 surveys, all sky surveys, and then go to the optical and to the telescopes, the optical telescopes. The models on the other side, up to now, predict that you have perhaps 3 or 4 times of these galaxies compared to observations. Not 10 or 100, but at least 4 or 5 more galaxies than we observe. So it still remains a doubt why we are not observing this. This is my opinion.
Thank you.
Thank you.
Yeah.
So let's thank again to Gaspar.
Thank
And
you very much to all of
the next speaker.
you for the patience. Thank you.